Welcome to the Bangalore seminar series. Today we have with us Dr. Rishi Saket from Google Research. So Rishi obtained his PhD from Georgia Institute of Technology in 2009 and followed it with postdocs from CMU and Princeton. He then joined IBM Research New York in 2011 as a postdoctoral researcher. Following this, in 2013, he moved to IBM Research India and he was promoted to senior research scientist in 2017. And then finally in 2020, he joined Google Research as a full-time research scientist. He's in learning theory, combinatorial optimization, and complex theory. Today, he is going to talk on his recent work on PAC bounds and intractability for learning from label proportions.
Thanks. Can you hear me? Okay, so PAC bounds and intractability probably people know a bit. So I'll talk about what this learning from label proportions is. I've given a talk on this topic last year in this seminar, but I think maybe there are other new folks around. So I'll introduce this problem and then talk about what we are trying to prove and why. So we all know probably the PAC model of learning, in which basically generally in supervised learning, what you have are training examples, which are feature vectors, and a label for each of those feature vectors. You can call them instances. In ML, they're called feature vectors, or basically they're vectors, right? And so given some distribution over training examples, right? X comma f of x, where f is the sort of the target function that you want to learn. You really want to efficiently output. You want to sample some of these examples and efficiently output a hypothesis which agrees with the target function with over the underlying distribution. Again, process should be done with high probability. This algorithm should run with high probability, and generally these functions are over the d-dimensional reals or with a d-dimensional Boolean space, and most of the time they are binary value. Right? So if this happens, we say that the class of such functions f can be learned by a class of the hypothesis class h. Right? For example, we know that linear threshold functions of half spaces, right, which is basically just the sign of r dot x plus c, right, can be learned. So it's basically just half space can be efficiently learned by half space. That's just a linear programming tool. Two-term DNFs, these are basically DNF formulas which are basically the OR of two ANDs, right? The ANDs are unbounded, but they're just two of them in an OR, right? They can be learned by degree 2 polynomial threshold functions, where a polynomial threshold function is just the sign of some polynomial, right? Of degree 2, right? So, but the problem is that nowadays, and in some applications as well, we may not be given the label of each of the feature vectors, right? I mean, because of, let's say, some privacy concerns, right? You don't want to reveal the training, maybe it's some medical domain or something, right? You don't want to reveal the label of some patient's medical history or something. Right?
Rishi,
so they may not. Hello.
Hello,
Yes?
a quick question. So are we also assuming the class is realizable or is in the previous slide? Is that what you were trying to? So I mean, does it belong to the
general? So in this PAC learning, the way I've defined it, yes, the examples come from x comma f of x. So that distribution over the training examples is realizable. Right? But there could be some noise sometimes, right? Those are more general situations.
Okay.
So, but I'll talk about the actual problem where we do assume that it's a realizable situation. Right. So, coming back to the motivation for this learning from label proportions, right? So sometimes you're not given the label for each of the feature vectors. I mean, this could be due to, generally privacy considerations. There could be legal considerations. There could also be some, the supervision could be costly or sort of ineffective. So it's sometimes very difficult to label each of these feature vectors, right? Maybe you can only use some aggregate label, right? So so this occurs in several applications. In images, sometimes you have the outcome of some collection of cells or something, the aggregate outcome, but you don't know the outcome for each of the cells in some high energy physics applications, etc. Also this occurs, right? So so this learning from level proportional framework is basically a direct generalization of PAC learning. So here the training set is consists of bags of feature vectors. These are just sets of feature vectors. So instead of one feature vector, you're given, let's say, 10 feature vectors and one label for each of these bags. And that label is supposed to be the average label of the individual feature vectors, right? So for example, I'll tell you that, okay, these are like 10 feature vectors and the average label is, let's say, 0.7, right? Which means that 7 of them are ones and 3 of them are zeros, but you don't know which one is 0 or not, right? But you still want to train an instance or a feature vector level classifier which agrees with this training set, right? I mean, which and also generalizes, right? So the goal is the same, but the data is of less fidelity now. Right? Earlier you had labels for each of the feature vectors, training levels for each of the feature vectors, and now you just have training levels for basically aggregate labels or average labels for bags of feature. So I'll talk about some results in this setting.
So Rishi is just wondering whether there's a partition that's pre-decided or the partition is random. I'm not sure whether that makes a difference.
So you're talking about these bags.
Yeah, the bags. Yes.
So I mean, you can assume that you are given some access to a distribution which outputs bags of feature vectors along with a label for each bag. So
right.
So I mean, it could be predefined, but you may or may not be able to see all of them together, depending on the situation. And there may not be a partition. I mean, it is like the bags could also overlap in general.
Oh, I see. So it's like sampling with replacement, kind of.
Not sampling with replacement. It's just that maybe I sample a bunch of feature vectors into a bag, right? And then I can resample those feature vectors or some of them into some other bag also.
I see.
So the bags themselves could overlap in general.
And
although there are applications, yeah.
And would it be the case that there has to be some stratified sampling over the feature space, or I mean,
feature
like
spaces
over the label space rather. Sorry. So I mean, do we have to assume anything about the big bags being approximately the same or anything like that?
not really.
Okay.
Like, I mean,
maybe
these could be like completely different bags. So you have, let's say, a collection of feature vectors. I am, instead of giving you the labels of each of the feature vectors, let's say I'm sampling a bag, and then I'm adding up the labels and giving you that, right? Instead of actually giving you individual feature vectors along with the labels. So you know the feature vectors, you just don't know the individual labels.
Got it. Thank you.
Yeah, so sometimes you don't have the actual. So for example, right, you have an image, right? Maybe it's like a medical image, and you know the average label of that image, right? I mean, maybe it's someone, some medical expert tells you that, okay, this image of an organ is like 70% diseased, right? But then that image is broken down into several small parts, and you really want to check whether that small part is diseased or not, right? But it's very difficult for the medical expert to look at these small parts and then tell you whether that part is, or maybe it's very expensive to do that. Maybe that person is very busy and can only look at that thing and just give a number that, okay, 70% of this organ is diseased, right? So you know the average label in some sense, but you don't know which of those things are disease, but you really want to still predict at those very small level. Maybe that's helpful for some reason, for example. Okay, so I'll talk about, so this talk is based on these two papers. So the first one is about learning half space of linear thresholds from these in this setting. And the second one is, so first one is about algorithm, second one is the hardness result for Boolean functions in this setting, learning Boolean functions. So I'll first talk about this one, right? So, as we heard, I mean, the PAC model is given as the following, right? But in the learning from level proportion setting, these training examples are actually backs, right? So they are backs of the form, let's say x1 to x3. These are feature vectors along with some label k. That, I mean, you can be the sum or the average, doesn't really matter because you know the size of the back. So so let's say it's the sum for convenience, right? So so it just says that the target function, right? Let's say it's the realizable setting. There is some function which is some labeling which is consistent with all the bags that you are getting, right? So there is some function which gives a labeling to these instances, so that the sum of the labels is k, right? So k is something between 0 and q. It's the binary 0-1 label setting, right? So in this study, right? So we assume that f is some unknown half space or a linear threshold function, just the sign of some r transpose x plus is just some half space, right? And our goal is to recover a close approximation to this f, right? Basically, a close approximation to r and c, right? So, I mean, in general, this problem is actually hard, right? So, in first of all, in the traditional supervised setting, right? If you have a bunch of examples in the realizable setting, let's say there's a half space that is consistent with all these examples, right? So you have feature vectors and labels, and there is some half space that perfectly classifies all these points. You can actually write a linear program and recover that. Right? You sample a bunch of points, write a linear program, recover that. So in that setting, it is half spaces are efficiently learnable up to arbitrary accuracy, right? But actually, in this LLP setting, right, this problem becomes actually quite hard in the worst case. So if you are, so I mean, I had some papers a couple of years ago. So if you have a set of bags, let's say each of size at most q, right, such that there is some half space which is consistent with these bags. I mean, their labels, right, their average labels. It is actually NP hard to find any half space which is consistent with more than 1/cube fraction of these bags. Right? So, for example, if you have bags of size 2, you cannot really satisfy, or it is NP hard to find a half space that satisfies more than half plus epsilon fraction of these bags. Right? So it's actually a fairly hard problem as soon as you have bags of size greater than 1. The bags of size 1 in a traditional supervised learning setting, it's actually an easy problem, right? But this hardness result is actually for worst case, right? You have an arbitrary collection of bags, basically an arbitrary distribution. But in real life, you can maybe sometimes assume that these feature vectors and bags are sort of randomly distributed in some sense. Right? So if you can assume, I mean, if you have some natural or well-behaved distributions in these bags, can you do better, right? So first of all, let's first see what a natural distribution looks like, right? So what would be a usually studied well-behaved distribution? So typically we assume that the underlying feature vectors are coming from some Gaussian distribution. So all the features are, I mean, the feature vector is sampled from some d-dimensional Gaussian, right? So something like NP sigma, right? So but you have, I mean, and then there is some labeling to these feature vectors given by some classifier, let's say a half space in our case, right? So, but how do you now translate this to the LLP setting where you also have to output random bags, right? So we define a random oracle, I mean, it's a bag oracle. So it's a distribution over bags of size q of a particular label proportion k over q, right? So fix k q, and you output a random bag of a label proportion k by q. So k1s and q minus k zeros, right? With the underlying distribution on the feature vectors given by this Gaussian distribution and mu sigma t, right? So what this oracle does is how it samples a random bag. So it samples k feature vectors from the distribution conditioned on the value of those feature vectors being 1. So d condition on fx being 1 and q minus k, and these are like IID, right? So you have a distribution where so basically if it's like a half space, then you sample from one side of the half space. You condition on one side of the half space, the positive side of the half space, you sample k random points from there, and from the other side you sample q minus k random points independently, right? So this will give you a bag of q feature vectors, and exactly k of them will be labeled 1 by that unknown, let's say, half space, right? So this is the sort of the random bag oracle that we'll consider. So let's say you are given access to this oracle, so you have this unknown half space, and you can access, you can sample bags of feature vectors, right, from this oracle. So you can sample a bunch of bags, but you want to actually recover that half space. You don't know that half space. All you know is that you can sample these bags, right? K by Q, yeah. So it is sort of a special case in some sense. But if you think of, let's say you have an oracle which can output a random label proportion, then you'll also randomize over K. So you first select a random K between, let's say, 0 and Q, and then output back with that label proportion, right? But firstly, one of the things is that if you have only K equal to 0 or K equal to Q, then these bags are not very interesting. All of them are labeled 0 or 1. So you can actually just sample those points. Even if you have just zeros, then you don't really learn much. Or maybe you can actually, in this case, probably you can actually recover very easily. But the more interesting case is K between K ranging from 1 to Q minus, right? Where then there is some uncertainty in the backside, which are zeros and which are ones. So but even then, you can have some random label proportion in that case. But you can, let's say, fix some K, right? So if you keep sampling, right, you'll hit a K with some probability. Right? So you can just use that one to sample those bags, right? But the results and the algorithm can be generalized to any, if you have a distribution over K also. But it's easier to just consider a fixed K for now, right? So so question is, now you have, let's say, K between 1 and Q, ranging from 1 to Q minus 1, and is fixed, but you can access these bags, right, which are sampled in this manner. So can you recover the unknown half space? That's the question. Okay. So let's look at a very special case where the Gaussian distribution is just N0I, so it's just centered at the origin, and the coincidence is just the identity, and K is not equal to Q over 2. Right? So Q is either odd, or if it is even, then K is not equal to Q over 2. So it's basically these are unbalanced bags. Right? So the number of zeros is not equal to the number of ones in the bag. So then there's a very simple algorithm, right? So you just sample a bunch of bags, right? And from each bag you sample a random feature vector, right? So you have now this collection of random these feature vectors that you have sampled. Now the main thing is to note is that the average of these feature vectors, as if they're sufficiently many, it actually starts aligning with the normal of the half space. So this is a homogeneous half space, so it passes through origin. It's just the sign of r dot x equal to c. Sign of r dot x, right? So that's what you do. If k is greater than q over 2, you just output the average, or if it is less than q over 2, then output the negative of that average as that normal vector r. You want to basically find the normal vector of the half space. Right? So why does this work? So it's actually not to think of a circle, right? And let's say the half space is some line, right? Something which separates the circle into two semicircles, right? So on one side you're sampling k points, on the other side you're sampling q minus k points. So let's say k is greater than q over 2, right? But they are uniformly sampled on that semicircle, and here also uniformly, independently sampled, right? So the component of the average, right, which along that line, the separating line actually will vanish, starts vanishing, right? So it's this thing, and what is going to be left is, because it's unbalanced, so something has to be left. It will start aligning with the normal to that line, so the R vector. I mean, it's actually not a difficult observation, right? So that's what happens, and then you have to sample a sufficiently large number of bags and vectors, random vectors from each of the bag, and then that expectation will give you that. You can recover the normal. It's a very simple algorithm actually. So this case is very simple. Oh, D is the dimension.
Question here.
Yeah.
Yeah. So in the previous slide, I was wondering whether the assumption on normal sampling is important. D being normal, is that important? And second question, is there some sort of difficulty? Because as you said, K being exactly Q, things become very easy, or K being 0, it becomes easy. And K being Q by 2, it's hard. So is there some sort of uncertainty or entropy variation with different K?
That I'm not sure, but for K equal to Q or 2, first of all, this algorithm that I said won't work because the whole average will vanish. Right? So you won't recover anything. Right, but there's still a way to recover that normal. The normal that R vector. Now, as far as why are we using Gaussian? First of all, it's a normal. It's a natural distribution, but I guess these can be generalized to anything which is symmetric in some sense, but it's sort of tricky. So, but we do use the properties of the Gaussian distribution to actually. It works out well in this case. Right? Otherwise, you'll have to look at how the distribution is symmetric and the convexity and so on. So that may be a bit tricky. But yes, but that's we could generalize this result to other types of distributions.
Thank you. Yeah, thanks.
Yeah, so this algorithm works, right? For very, very simple situation where it's just a standard Gaussian distribution centered at origin, and K is not equal to Q. Very simple algorithm. What happens when, let's say, we still consider just the homogeneous linear threshold, so no constant term, but let's say you have a general covariance matrix, but still centered at all for now, right? So and of course K can also be Q or 2, right? So we don't want to. That question. That part also we want to take care of, right? So the first thing to observe is, let's say you have a bag, right? It's a bag with K1s and Q minus K zeros, right? So if you sample 2 points from that bag independently, right, then the probability that those points have different labels is exactly this quantity, which is 2 times K times Q minus K over Q squared. So that Q squared pairs, and this is the probability, right? But if you sample without replacement, that probability changes, right? So there is a slight nuance between sampling with and without replacement, right? And this ratio of these probabilities, right? So if you, let's say, if you use the true classifier, right, which is R dot X, the sign of R dot X, right? Turns out that the ratio of this, you can compute this ratio for any labeling given by any classifier, right? For the true classifier, this is going to be those values, right? So if you use the actual classifier, this is exactly going to be the value, because they're going to be Q minus K, K1s and Q minus K zeros. And so this is exactly going to be the value for sampling independently and sampling without replacement, right? So the ratio, so this is actually slightly higher. So the ratio of this to this is maximized. Is actually what we show is that it is maximized if you use the true classifier. But if you use something which is away from the true unknown classifier, then this ratio becomes smaller and smaller. Okay? So basically, you can define this quantity, the variance of R transpose of Z1 minus Z2 where Z1 and Z2 are sampled divided by the variance of R transpose X1 minus X2, where X1 and X2 are sampled with replacement, basically IID, right? Then you can show that this quantity is actually maximized when R is either plus minus R star, where R star is the actual normal to the actual half space, right? And yeah, I mean, it is not a proof sketch, but basically what you show, you can actually compute this for N0 I. So it's not that difficult to compute. And it also depends on K. So let's say for K equal to Q over 2, what you get is this quantity, where it's 1 plus 1 over something positive times cos square theta, where theta is the angle between R and R star. So let's say these are the factors, right? So, and of course, this is maximized when cos theta is either 1 or minus 1, which means R should be equal to R star. So this actually you can prove, it's not a very difficult exercise, right? So, but for the special case of N0 I, and K is equal to Q over 2. So basically, if you look at what's happening here, so variance of R transpose Z1 minus Z2 is this yellow thing. Variance of R transpose X1 minus X2 is something like this, and this is the line along which that thing and the ratio is maximized. I think some maybe it's the wrong color. So you want to maximize this. And this blue line is the separating plane, and green is the normal. Okay, so this happens, and therefore basically what you do is you can estimate this quantity, right? You sample many bags. You can estimate the top quantity by sampling a lot of bags and then sampling pairs of points without replacement, and then the bottom quantity by sampling lots of bags and then pairs of points with replacement. And you can estimate this. You have to use some convergence bounds and so on, and then you can compute. I mean, so then it's actually, so this thing you can estimate as some sort of a matrix here also as a matrix, and then you get an expression in terms of the principal component of some matrix. So I'll give you that expression, but you can basically do this distribution using sampling, right? And what happens when you have a general, a covariance matrix? It's not that simple, so you have to work it out, right? So yeah, so what you get is this quantity here, right? So so this rho quantity is something like 2 plus gamma R squared times kappa 2 times 1 minus divided by 1 minus gamma squared times kappa 1, where kappa 1 is greater than or equal to 0 and kappa 2 is strictly greater than 0. And this works for any k between 1 and q minus 1. As I said, the k equal to 0 and k equal to q are uninteresting. So we just look at k from 1 to q minus 1. And these kappa 1 and kappa 2 depend on q and k. Right? So q is greater than or equal to 2 always. And k is something here. And then this gamma r is defined as this, right? So you take this sigma, take the square root of sigma. So sigma is a positive semi-definite matrix. It's a covariance matrix, right? So you can always take a square root of a PSD matrix. So you basically do the eigen decomposition, take the square root of the eigenvalues. That will give you that. So you do that, and then you look at that as a linear transformation times r, and that as a linear transformation times r star, and the angle between them, right? So this is actually cos of that angle, not the angle itself. So and then you have this term. So basically, again, when r is minus or plus minus r star, this is maximum. You assume that the covariance matrix is non-singular, and that will give you. Any questions on this? I mean, you can actually, this is not again that difficult to prove. You can actually try to prove this, and yeah, you can this. So this also works for any value of k, and you can recover this. So basically, the algorithm, and in general also this works. So what you do is that you define this matrix sigma b, which is expectation of the covariance of x1 minus x2. Sorry, this is the covariance of I mean, so this is some covariance matrix, right? So this is expectation of x1 minus x2, x1 minus x transpose, and sigma d is the same for the z point. So this is x1 and x2 are sampled. I think there is some notation inconsistency. I think so. These are sampled with without replacement. These are sampled with replacement, and then you look at the R max of. I think this should be sigma d upstairs and sigma b downstairs, right? But so you basically you want to look at the one that maximizes this ratio, just the thing that I mentioned in the last slide, and you can actually write this as some principal eigenvector computation, right? Maybe the notation is slightly wrong, but that's what it is, right? So and then sorry, so what you can show, so you really need to compute these matrices, right? I mean, of course, you cannot really exactly compute them because you can only sample bags and sample these feature vectors from bags and then compute them using those samples. But you can actually do that approximation and get sigma b and sigma d sufficiently with estimates of sigma b and sigma d sufficiently accurate so that you can recover the I mean do the recovery, right? And there are some issues that you also have to deal with. For example, all you get is the direction or the negative of the direction. So you need to figure out which one is the correct one, and then you can use a bunch of other samples on the bags to actually figure out which is the correct direction. That will only work if k is not equal to q over 2, because if k is equal to q over 2, the correct half space as well as its complement actually satisfies it. So if you're in the unbalanced bag space, you need to get some sort of a sample error bound, and then from that some generalization error bound. So there are a bunch of generalization error bounds that you need to use. And for the estimation part, right, you use some sub-Gaussian concentration bounds for thresholded Gaussian. So these are not exactly Gaussians; they're slightly different distributions, but they still satisfy sub-Gaussian property, right? Because I mean, when you sample a feature vector from a bag randomly, you're not really sampling from a Gaussian distribution. You're sampling from one half of the Gaussian with some probability, like k over q, and the other half with probability like q by sk over, right? So it's an unbalanced sort of Gaussian distribution, unbalanced with respect to some threshold. But that still is sub-Gaussian, and all you need is some sub-Gaussian concentration bounds in that. You need to prove they're sub-Gaussian. That's a bit of a boilerplate exercise. Yeah. So this is how these algorithms. Any questions?
Yeah, I was.
Yeah.
Sorry, quick question. So I was wondering whether the eigenvectors are always real, or rather the eigenvalues are always real, and is that a consideration at all?
Yeah, no, eigenvalues are always real. These are real matrices, real symmetric matrices. The eigenvalues are always real.
Oh, okay. Sorry, I missed that. Yeah. Thanks.
Okay. So okay, this is just describing the actual bounds that we get. So the first case is where you have the simple case where you don't have to estimate any covariance matrix or anything. It's just a sampling and an average. So over the samples, in that case, what is written in this order notation is the number of samples that you need, and after that there is some polynomial time processing, which is basically sometimes just computing some principal eigenvector or something, right? So in this case, the first case, the number of samples is basically d over epsilon squared, where epsilon is some sort of error that you want, log d over delta, which is the probability that you want success, where delta is the probability of success. This is just the PAC learning bound. And but when you are in the other cases where you have to estimate these matrices, then the bound worsens a bit. And it also depends on the eigenvalues of that matrix, because if the matrix is really bad, right, it's difficult to estimate that. So I mean, and in the more general case, they're like problematic. I mean, it's a very complicated expression. But if all these parameters are reasonably okay, then you get efficient algorithms. So how are we doing on time? Any questions on this part? So in the last thing, you also have, I mean, it's a general Gaussian, so it has a mean, as well as the half space is non-homogeneous, so there is a constant also, C star, both of which you have to estimate. So there is another algorithm to estimate the constant, but it's again some sort of combinatorial algorithm, but you can do it. So next thing I'm going to talk about is the hardness, some hardness results on learning Boolean functions from level person. This joint work with which appeared in this statistics. Okay, so in this case, yeah, we saw, I mean, PAC learning algorithm when you have some distributional assumption on the feature vectors in case of half spaces, right? But in general, you may not have any such assumption. So we are looking at worst case scenarios in this case, and you really want to learn an accurate instance level classifier in the LLP setting. But generally, what happens is you really optimize on the training data. And how do you optimize on the training data? You optimize some loss on the training. That's what you do. In this case, the training data is just a bunch of bags with their label proportions, right? So one way to optimize your model on the or basically classifier on the training data is to classify these training bags, which means that satisfy them. You want to satisfy the label proportions of as many training bags as possible, right? So this is the optimization problem that we're, yeah. Yes, sir.
So I was wondering if you wanted to look at worst cases as compared to the last case, what type of things you might want to be adversarial in. So you might want to be selecting the bags in the worst possible way, given the algorithm. Is that the worst case you're looking at?
Essentially, yes. So you can have your underlying set of feature vectors, and then the bags are basically adversarially selected, essentially.
Okay. And in the previous case, they were Gaussian. That's the main difference, right?
Yeah, so Gaussian was the distribution of the feature vectors, and then the bags are selected. I mean, I guess Gaussian, I mean, the bags themselves are in a way then Gaussian in some sense, right? So basically, the underlying feature vectors are Gaussian, and then the bags are selected in this manner that you sample K from uniformly from the distribution restricted to 1 and Q minus K from the distribution restricted to the value 0.
Right. Okay, thank you.
So, but here in this worst case scenario, you have no control over how the bags are.
Yes. Yeah, and so this is probably much harder because given your algorithm, the adversary can choose it badly for you.
Yeah, absolutely. Of course, you can look at what the choice is and the bunch of bags that you're getting, and then design your algorithm after that. But I mean, not design the algorithm, but we look at it. Your algorithm can look at that, but yeah, it is difficult. So yeah, we show some hardness.
Thank you.
Does that answer your question?
Yes, thank you.
Take a sample from the bag. So
yeah, I mean, you're given the bag. You're given all the feature vectors in the bag. You don't have to, there's no distribution associated. You're just given them explicitly. So this is like 10 feature vectors, and there's this label proportion for this bag. Yeah, you're not given the individual, obviously then. So yeah, so yeah. So in this case, you really want to optimize on the training set of bags. It's just a bunch of bags, and you want to fit your class. You want to classify as many bags as possible correctly. You want to match their label proportion. So yeah, I mean, in this setting, so this is a set space of feature vectors. In this case, we'll just consider Boolean, d-dimensional Boolean feature vector, and you have these bags which are just some subsets, and this. Yeah, for a given classifier, there's a label proportion for each bag that it induces, right? And you want to you have these training examples to train H, which is consistent with F in terms of the bags that it is satisfying, right? So we say that the hypothesis satisfies a bag B if the label proportion induced by the hypothesis is same as the label proportion that you're given, which is consistent with some unknown target function. That's the way we define back satisfaction. Right. So yeah, so you're given these bunch of bags and you want to find the hypothesis maximizing the number of satisfied bags. So this is a bit of a strict consistency requirement here. That you want to exactly match the label. It makes sense for small bags. I mean, if you have a bags of size 2, you pretty much want to match the label proportionally, right? Or your bags of size 3 or 4. Basically, it makes sense. For larger bags, you could have more general notions where you may want to have the label proportion given by the hypothesis be close to the actual label proportion, and you can have some sort of a loss between them. But we'll just look at consider this strict case. Okay, so what do we show? We look at the learnability of Boolean formulas in this setting. Right. So we look at hardness of learning the OR formula, the very basic Boolean formula, right? So if you are, and just for bags of size 2, if you are given a bunch of bags, right, B1 to Bn, right, where each of the bag is of size at most 2, and f is the target function is some unknown r, some unknown OR function. So all the labels are all the label proportions are consistent with this unknown OR function, right? And you want to recover it, right? So what we show in the first result is that you can even use a constant clause CNF. So a CNF formula is just an AND of ORs, right? So it's an AND of clauses. Each clause is just an OR of some literals, right? So if you can use up to like 100 clause CNF, any constant clause CNF, right? Or is of course a one clause CNF. So you can use that, but you can still you won't still be able to satisfy even any delta fraction of the bags. It's hard to do that. Okay? So it's hard to use even 100 clause CNF to satisfy even a tiny fraction of the bags. That's the first result. And in the second result, we show that you can use a different type of function, which is a constant width DNF. So DNF is an OR of ANDs. So OR of these terms, each term is an AND of literals. The constant width DNF is one where the width of each of these ANDs is bounded by some constant, maybe 100 or something. And in particular, OR is just a one width AND, one width DNF. So because each of the terms is just one literal. So even that you can use a constant width DNF, and then you can satisfy more than half of the bags. Right? Both these things are NP-hard. So and you can contrast this with the usual PAC learning case where you fully supervised case where OR can actually be learned by OR itself. Right? You don't need anything else. And it's a very simple algorithm also. Right? And also, if you have bags of size at most 2 like this, you can actually find a half space which satisfies 40% of the bags. In fact, you can for learning half spaces with half spaces or LTFs with LTFs, basically. In the LLP setting, you can, for bags of size at most 2, you can have an accuracy of 40%. So you can satisfy 40% of the bags, which means that OR can also be satisfied by a half space. I mean, OR can also be learned by a half space with accuracy of 40% on bags of size 2, because OR can be captured by a half space, just a half space, actually, a very special half space. So this actually shows, the first result actually shows a separation in the sort of the power of OR versus a half space. So OR or even a constant clause CNF, right? So constant clause CNF cannot satisfy even delta fraction of the bags of such bags, whereas you can use a half space to satisfy 40%. So it shows a bit of a separation there.
So I'm trying to understand the first result. So it means that the representation power of the CNFs, constant clause CNF, is probably quite low. Does that mean that is the problem that you are using constant clause rather than polynomially many in M? Is that the issue?
Yeah. So if you use polynomially many, maybe you can do better. That is not clear. But constant clause, I mean, the representation power is definitely more than an OR, right? Because it captures an OR definitely, right? But maybe it is not amenable to designing such learning algorithms in the LLP. That's basically what it means. It is not sufficiently powerful for learning algorithms to admit learning algorithms in the LLP set.
Right. Okay. Thank you.
And the other thing is that if you look at the real version of the first result, that's actually not known. The real version of the first in the real space, that would mean to showing that a half space cannot be learned by the second result. So the second result, the real version of the second result would mean that a half space cannot be learned by a polynomial threshold, right? Because you can think of a constant width DNF as a constant degree polynomial in the real space, right? But no such result in the real space. Basically, learning half spaces in polynomial thresholds is actually right. So the second result is sort of says that maybe it is possible to do such thing in the real space, but in the Boolean space, such things do not, and such hardness works. So this is an open problem. What?
First question. Constant plus CNF satisfying delta function is difficult for any constant, but sub constant
could be, yeah, sub constant probably.
Algorithmically anything known already, like.
No, actually, nothing has been studied really here. Right? So people have not studied this algorithmically. But the only thing that is known is this thing, that you can use a half space to satisfy 40% of the bits. That's known. There's one more result for batch of size 3. I talked about that last year. So it is much more complicated actually than this one. So yeah, that's many of these, most of these questions are actually open.
Just to understand the Saket 21 result, it is in the adversarial setting that you can still learn 40%. That is, adversarially, if the bags are chosen, still you will satisfy.
Yeah, you can. It's a semi-definite programming based algorithm. So you write an SDP, round it, and you can get a half space which satisfies 40% of it. Assuming that there is some half space that satisfies all of them, that unknown half space.
I see. Okay, thank you.
Okay, so yeah, so and the third result is about learning parity, right? Which I'll talk about a bit more in slightly more detail, right? So here, so the target function is just a parity. So you have Boolean feature vectors, right? And the f is just a parity. So it's just given by the XOR of some bunch of feature values and possibly XOR with one. That's the constant part of the parity. Basically, it's a linear form in F2, right? So here, if the first result shows that it is NP hard to find a parity which satisfies. So if you have bags of size q, so q over 2 to the q minus 1 plus delta fraction of the bag. I mean, anything greater than q over 2 to the q minus 1 fraction of the bags cannot be satisfied, right? There is an algorithm to satisfy 1 over 2 to the q minus 2 fraction of the bags in polynomial time. Okay, so let's look at that thing. So first of all, if you have, I mean, again, in the fully supervised case, right, where you have the actual labels, parity can be easy. I mean, just you have to just solve something over GF2, a linear system over GF2, and I mean, field of size 2, and you can get it. For bag of size 2 also you can, right? Because for bags of size 2, it's actually, so if you know the label proportion right, so it's just bag of size 2, right? So the label proportion is either 0, half, or 1. If it's 0 or 1, the parity, you know the parity, right? And which is 0. And and if the label proportion is half, you know the parity, which is half. So you can just solve a linear system. It's actually a affine system, and you can actually satisfy all the bags. So for q equal to 2, there is no hardness, bags of size 2. But as soon as q becomes bigger, you do get the hardness. But there's still a gap between the algorithm and the hardness. It's not exactly matching. Okay. So I'll just sketch a proof of how do you a part of the proof of this result. Okay. So so the main thing, the main part of such hardness results is what is called a dictatorship test, right? And that actually is combined with what is a known hard constraint satisfaction problem, and then you get the hard instance of the problem that you're interested in. This is a usual general template of proving hardness results, right? Yeah, and yeah. So and then this combination requires some tricks, but the main core of most of these hardness results, I mean, this is not a particularly complicated one, right? It's just is this dictatorship test. So what exactly is a dictatorship test? It's basically a toy instance of your problem. In this case, it is this LLP problem of parity from BACs, right? Right. For over some, so it is a problem defined over some large domain M. So let's say M is a dimension, right? And it has two properties. So it's a toy instance. So it's just a collection of bags, right? With a level proportion for each of these bags, right? So the completeness shows the completeness property means that if you select any coordinate I, there must be some parity or some solution, right? In this case, our solution is this parity function itself, which satisfies all the bags, right? And the soundness means, I mean, implies that if you have any parity which satisfies more than that hardness factor fraction of the bags, then it must be supported on a very small fraction of the coordinates. That parity cannot, I mean, parity is defined by a small fraction of the coordinates. It cannot, that set of coordinates defining the parity should be very small. It should be independent of this capital M and depend only on Q and this delta. Right? So these are two properties, right? And we want to construct this. This is called the dictatorship test. So we'll just go over this. Right? So the dictatorship test is given by this bunch of bags. You can actually just define it by a distribution on bags. So bags of size Q. The set of feature vectors is all the Boolean feature vectors of dimension capital M. Right. So how do you sample a bag? So you have to sample Q feature vectors. So you sample x1 to xq, where for each of the coordinates you sample that row. So you think of these feature vectors as columns of a matrix, right? So each row is sampled uniformly from the set of vectors which have exactly 1, 1, right? And the rest Q minus 1 zeros, right? So you want to EQ, that's the coordinate vectors. You just sample each row uniformly from that set, and then that will give you your random vector, right? And the label, the average label of that bag or the label proportion is just 1 over Q. So that's your dictatorship test. Now, clearly, if you choose any coordinate I, then you just look at the parity given by just that particular variable, that particular coordinate. Fi xi is just fi of x is just xi. That satisfies all the bags because that row exactly has 1, 1 and all zeros, right? So so it has a label proportion of 1 over. So all the bags are satisfied. So completeness is clear. The question is soundness, right? So suppose yeah. So suppose that there is some parity which hx given by some subset S, right? Where just for convenience, let's assume that K is odd. The size of that set is odd, right? Capital K is odd. And then we need to show the soundness property, right? So basically let's say you have this hypothesis, right? So you can write this. So you have this bag B which is sampled randomly from the distribution, and then you look at So if you look at the parity given by all of these this thing, right? So it is basically you're summing up over all these feature vectors. So you can take that set out, this part out first, and then look at this thing. You can just reverse the XORs here, right? And then this means that so this part, right? So this part is actually equal to 1 because so why is this? Because you are basically looking at one coordinate and summing up all of this, that particular row, right? This is the XOR of that row. So that part is just one. So it is just a sum. I mean, it's just an XOR over odd number of ones, which is one, right? So the parity of, I mean, if you look at the parity of all of them, it has to be one, right? And yeah, so and now so the parity is always one because k is one. That's the main thing. Now suppose that this thing right over so you sample this bag and these few feature vectors, and this vector of length q given by h of x1 till h of x3 is close to the uniform distribution on the parity one subset of 0, 1 to the q, right? Because you know that the parity has to be one, right? So if this thing distribution itself is very close to the parity one subset of 0, 1 to the q, then what is the probability that there is exactly 1, 1, right? That's, I mean, the size of the parity one subset of 0, 1 to the q is 2 to the q minus 1, right? And the q possibilities of exactly having 1, 1, right? So that's just q over 2 to the q minus 1, and basically that is the probability that the bag B is satisfied, because that was the level proportion 1 over q that you want to hit, and there are only q out of 2 to the q minus 1 possibilities of hitting that. When this is close to a uniform distribution, that's the probability you get. So this is fine. So the key thing is to prove that this is close to the uniform distribution on the parity one subset of 0, 1 to the that is bag B sampled according to the distribution we created. So I'll just finish this. Okay, so how do we prove this part that it is close to the uniform distribution? The first thing, the first line. It turns out that it suffices to show that for any subset T of 1 to q, where the size of T is less than q over 2, at most q over 2, and greater than 1, the if you just look at the parity of that subset with respect to the h of, so basically at parity of h of xj, where j is from that subset T, if this is unbiased, so the probability that this parity is equal to 0 is half, holding for all these subsets, then you're done, right? Essentially, basically what it means is that I mean, okay, so that it goes into the Fourier analysis and stuff, but basically it boils down to proving this, right? So how do you prove this part, right? So you define this this variable. So what this variable is doing is you are looking at only the so you're looking at only the ith row in this case, right? So only j of the only t of the columns you're looking at, and the ith row, right? So this means this is looking at I mean only t of the columns, right? So you're basically looking at the parity of h of xj for j in t, and then here you are looking at only the part of that parity given by the ith row, right? So now if you look at this, so you have this, you're looking at only only t columns and just one row, the ith row. And in that row, you know that there is exactly 1, 1, but it could be randomly in any position, right? So which means that this zi is 1 with probability r over q, where r is the size of this set that you're looking at, I mean the column that you're looking at, and 0 with probability 1 minus r over q, right? That's the way you constructed this distribution, right? And then the XOR of x, I mean this XOR that you're interested in is just the XOR over all the zi's for I in S, right? So you look at the H is supported only on this particular set, so you look at only those rows, right? So now how do you sample? And the other thing is that each zi is independent of each other, right? So another way of sampling these zi's, right? So each zi is is 1 with probability r over q and 0 with probability 1 minus r over q independently, right? So what you first, I mean, another way of sampling these zi's, you sample a subset u of s by choosing elements with twice this probability, 2r over q, and 2r over q is at most 1, right? And then for I within that, outside that subset, you set them to 0. And inside, you set them all independently, one with probability half. That's the same distribution that you have here, right? So this is the way to do it. Now the thing is that it's not too difficult to show that if the subset U that you have sampled by choosing everything with probability independently with probability 2R over Q, if that is non-zero, then this XOR is unbiased, because then you have a random flipping of some non-zero number of variables, right, in a non-zero set, and the XOR then vanishes, right? And then that probability is actually very, very small. So basically, the probability that this U is empty, so you're sampling everything with probability 2R over Q. So the probability that U is empty is 1 minus 2R over Q to the power of K, right? And then this becomes very, very small, right? When K is larger than this quantity. So as soon as your parity is supported on a large enough set, basically it's unbiased, and then basically you have proven that you cannot satisfy backs with probability greater than Q over 2. Completes the proof. Yeah, and yeah, so the other hardness reductions, I'm anyway not going to talk about them, but they basically for the DNF formula and CNF result, they use some bipartite label cover and some dictatorship tests. Basically, some reductions are adapted from some work from long. That was for the visual supervisor. Anyways, so yeah, you just go over some. I mean, mostly everything is open in this domain, in LLP domain, from the computational learning setting, right? So this PAC learning for polynomial thresholds, Boolean functions with distributional assumptions. I mean, people have not looked at the hardness results for learning half spaces with polynomial thresholds. Again, not looked at in the traditional supervised setting, right? Of course, half spaces can be learned by half spaces without noise. But in the adversarial noise case, now we know, I mean, that you cannot learn half spaces in the presence of adversarial noise using even degree D polynomial thresholds. But though that sort of result, translating it to LLP, in this case, you don't even need noise, you have bags, right? That's not known. Now, algorithmic guarantees for learning LLP learning odds that you mentioned, right? Maybe instead of delta, you can get 1 over log n or something like that. Again, not known. Basically, all of these are open. And in the last case for the parity problem, the algorithmic and the hardness bound, they had some gap. So that's again open. And all of these problems are many bunch of other concept classes, decision trees and so on. Everything's open. Okay, thanks. Any questions? Thanks.
Yeah, sorry, I have a question. I'm not sure whether
sure.
Is that okay? Yeah, so
Sure,
quick
sure.
question. So I was wondering whether some of your results mentioned that you cannot learn it beyond a threshold delta, and this was independent of the number of samples you have. So I was wondering whether even asymptotically, you cannot make statements that if I sample infinitely, I will be able to learn something. And that was surprising to me. So can you tell me why that happens, or what setting that happens in the lower bound?
No, so in the lower one, you usually don't even have a distribution. I just give you the entire set of bags, right? So the support of the distribution I gave you, basically. And you can sample from that if you want to, but it's just the support of the distribution. It's just, let's say, M bags, right? And in polynomial time, in the size of that input that I've given you, cannot do better than some. That's what you should.
Yeah, I'm actually talking about the second part of your result. So there you mentioned that you cannot learn with DNFs of constant size anything more than delta fraction.
Yeah.
So I was wondering, is that a problem of sampling, or is that a problem
Rahul,
of
there is a colloquium right now. we have to take this offline. So
Okay.
I'm sorry. I'm
yeah,
sorry.
people
Sorry
are
about that.
waiting out.
I'm very sorry. Yeah.
Well, thanks.
Yeah,